So in this lecture, we will be dealing with some additional numerical problems. So let's start. So now suppose, um, let me write the question. A horizontal bar is fixed at one end, is fixed at one end where the x coordinate is equal to 0, and the length of the bar uh, is 1 meter. And the cross-sectional area of that bar, the cross-sectional area of the bar is 100 millimeters square. And it has varying Young's modulus with respect to x, which is equal to 100 e power minus x GPa, which is valid only when x is in meter. So we have to find the displacement at free end. We have to find the displacement at free end in millimeter. So this is a question. So let's first visualize this schematic diagram of this given question. Okay. So the schematic diagram looks something like this for our given question. This is the fixed end, and a horizontal bar is fixed at one end. So this is the horizontal bar which is fixed at one end, and here the x coordinate is equal to 0, and here x equal to 1 because the length of the bar is 1 meter. And this bar is subjected to a load of 10 kilonewton. So we have to find out the displacement at free end, that is at this side, how much the bar will displace. So firstly, now suppose bar is free from both sides. Suppose bar is free from both ends, this ends and this ends. There are no restriction to the bar, and then load is applied, and then load is applied, and then load is applied. So the condition will look something like this thing. So the bar is free from both ends. So this is the initial configuration, and when the load is applied, then there will be some elongation and deformation in bar, like this thing. So this is the final configuration when the load P is applied here. So, so suppose the elongation from both sides will be 5 millimeter, and here also will be the same elongation, 5 millimeter. So total elongation will be 10 millimeter, but this so displacement at each end at each end will be 5 millimeter. Okay, so this was the just overview that how we are going to tackle this problem. So now if bar is fixed at one end, so this is the condition. Sorry. Now bar is fixed at one end. Now suppose bar is fixed at one end, then displacement at free end, then displacement at free end, is equal to elongation. Now let's solve with the given equation. We know that for varying quantities we are going to use this equation, that is delta L equal to integration 0 to L P dot dx divided by EA. So here P and A are constant and Young's modulus is varying. So value of Young's modulus is 100 into e power minus x. So 0 to 1, that because initial length is 0 and final coordinate of the bar is x equal to 1 meter. So it will vary from 0 to 1. Now dx upon 100 e power minus x. So substituting the value, delta L is equal to 10,000 Newton, that is 10 kilonewton, divided by 100 millimeters square per GPa. 0 to 1 dx upon 100 e power minus x. So delta L is equal to here will be 10 power MP upon GPA, that will be 10 power minus 3, 0 to 1 e power x dot dx. So we can write it as 10 power minus 3 e upon 0 to 1 e power x 0 to 1. So substituting the value, we are going to get 2.718 millimeter minus 1, so which is equal to multiplied by 10 power minus 3, so which will be equal to 1. This will be not 10 power minus 3 because we have already multiplied it inside. So the answer will be 1.718 millimeter. So this is the solution for this question. Now moving to the next question. Let me clear this thing up. Now moving to the next question. So suppose there is a prismatic rod which is supported in a bearing at one end. Um, so this is the bearing, and this is the prismatic rod which is supported at one end at bearing. And in the bearing, in the bearing, in the bearing, the rod is rotated at about horizontal plane with constant angular velocity. With a constant angular velocity, we can call it as omega. So we have to determine the stress at x location and total elongation. So suppose we have to determine the stress at x location. So firstly we will draw some axis plane here for reference. Now we have to find out um, the stress at x location, that is here at x location. So the total, so this is small x, and we can assume that is this full thing is capital X, and this length will be L minus Ax. Or we can take it as not x, so it will be L minus x. It will be total L. So in this case, the effect of self weight will be neglected. So here we have learned that either in order to calculate the actual loading, we have to consider either side of the section. So we can consider this part, this side, or this side. So just remember that we have to always choose the free end, that is this free end, to calculate the stress, because minimum unknown are there in this case. So load at x is equal to px, which is the summation of the load of either side, load present on either side. So suppose the member is fixed. Suppose the member is fixed. We have to find px from the free side. From the free side. So we know that Fx is equal to mr omega square. So we can write mass in terms of density into volume, r omega square. So we can write here density into A into L minus X, or which is main parameter to be find out. This is the main parameter which you have to find, omega square. Now suppose just we have to consider this section. So suppose we have to consider this section only. This is axis, okay, and the center of mass must be located at somewhat here, and there is a uniform distribution is a mass. There will be a uniform distribution in the mass. There will be a uniform uniform distribution in a mass, uniform mass distribution we can say, and the length here is the L minus x, and so from center of mass this length will be L minus x by 2. So here R we can write as in this equation equal to Px is equal to rho A L minus x. So the value of R will be x, that is x plus L minus x by 2 multiplied by omega square. Now moving forward, after simplifying it, after more simplification we are going to get Px is equal to rho A L square minus x square omega square by 2. So we can find the sigma x is equal to Px upon Ax, which will be rho A L square minus x square omega square by 2a. So a will cancel out, so we are going to get the value of sigma x equal to rho in bracket L square minus x square omega square divided by 2. So this is the expression for sigma x. Now in order to calculate the delta L value, I have to clear some few things. Okay, so in order to calculate the change in length, that is delta L value, we will use this equation of varying quantity, that is 0 to L sigma dot dx upon E. So we will write rho omega square upon 2E 0 to L upon L square minus x square dot dx. So after further simplification we are going to get rho omega square by 2 L square x minus x cube by 3 by 0 to L, and after further simplification we are going to get rho omega square by 2e L cube minus L cube by 3. So after further simplifying we are going to get rho omega square by 2 2L cube by 3, and at the final equation we are going to get for delta L is equal to rho omega square L cube by 3e. So this is the final expression for change in length. So this marks the completion of the first section, and we'll start the second section by tomorrow. So for now, thank you.